Scene script. Have you ever wondered why some medicines dissolve quickly in your body, while others take longer? This is not a question of mere manufacturing or formulation, but one deeply rooted in the science of solubility and distribution phenomenon. What is solubility, you ask? Simply put, it's a measure of how much of a particular substance can dissolve in a specific amount of solvent. In the realm of pharmaceuticals, it's a crucial property that impacts how fast a drug can be absorbed into the body system. If a drug is highly soluble, it will dissolve quickly, making its therapeutic effects more promptly noticeable. Conversely, a poorly soluble drug may take longer to exhibit its intended effects. Now let's talk about the distribution phenomenon. This term refers to the process by which a drug travels from the bloodstream to the site of action. It's a journey, if you will, that takes into account the drug's chemical nature, the body's physiological state, and the interaction between the two. The distribution phenomenon is a fine dance between the drug and the body, one that determines the drug's effectiveness and the duration of its action. These two phenomena, solubility and distribution, are so significant that they form the basis of the Biopharmaceutics Classification System, or BCS. This system classifies drugs into 4 categories based on their solubility and intestinal permeability. This classification helps pharmaceutical scientists predict how a drug will behave in the body, guiding them in the development of more effective and safer medications. So, the next time you pop that pill or take that syrup, remember that there's a world of science operating behind the scenes, determining how quickly the medicine will dissolve, how it will travel in your body, and how effectively it will do its job. Understanding these phenomena is crucial to the development and use of effective medications. So, what exactly is solubility, and why is it so important in pharmacy? Well, imagine you're making a cup of tea. You add sugar and it disappears, dissolves into the hot water. That's solubility in action. In the world of pharmacy, solubility refers to the ability of a substance, in this case a drug, to dissolve in a specific liquid known as a solvent. Now, why is this important? Let's think about the journey a drug takes in our body. It's swallowed, enters the stomach, dissolves, and then is absorbed into the bloodstream. If a drug can't dissolve properly, it can't be absorbed effectively, and it won't reach the site where it's needed. So, solubility plays a crucial role in how well a drug works in our bodies. But what influences solubility? Several factors come into play here. The nature of the drug and the solvent, temperature, pressure, and pH can all affect solubility. For instance, some substances dissolve better in hot water than in cold, which is why we use hot water to make that cup of tea we mentioned earlier. In the case of drugs, many are designed to dissolve at specific pH levels found in different parts of the body. Some drugs are more soluble in the acidic environment of the stomach, while others dissolve better in the more neutral environment of the small intestine. This brings us back to the role of solubility in drug effectiveness. A drug that doesn't dissolve well may not be fully absorbed into the bloodstream, reducing its effectiveness. On the other hand, a drug that dissolves too quickly may be absorbed too rapidly, leading to potential side effects. So you see, solubility is not just about dissolving. It's a critical factor in the design and function of drugs, influencing how they're absorbed, distributed, and how effectively they can treat the conditions they're designed for. The solubility of a drug can greatly influence its absorption and distribution in the body. Now that we've understood solubility, let's delve into the distribution phenomenon. The distribution phenomenon, or as some like to call it, drug distribution, is the process by which a drug is dispersed or distributed throughout the body. It's like the postal service of your body, ensuring that the letters, or in this case, the drugs, reach their intended destinations. So how does this work? Well, once a drug enters the body, it doesn't just stay in one place, it moves around, reaching different parts of the body through our bloodstream. This is what we call the distribution of the drug. But here's the catch. Not all drugs are distributed equally. Some drugs may prefer certain types of tissues over others. For example, fat-soluble drugs are more likely to accumulate in fatty tissues. On the other hand, water-soluble drugs are not as likely to do so. This preference can significantly affect the concentration of the drug in different parts of the body. Now, let's add another layer to this. The distribution of a drug is not just determined by its solubility, it's also influenced by factors such as blood flow, capillary permeability, and the binding of the drug to plasma proteins and tissue receptors. What does this mean for us? It means that the distribution phenomenon plays a crucial role in determining the effectiveness of a drug. If a drug doesn't reach its intended destination, or if it gets stuck in a part of the body it's not supposed to, it may not have the desired effect. Let's take a step back and look at the bigger picture. The distribution phenomenon is a complex, dynamic process that affects how a drug interacts with our body. It's not just about how much of the drug is in our body, but where it is and how it's moving around. In essence, understanding the distribution phenomenon helps us predict and control the effects of drugs, leading to more effective and safer drug therapies. The distribution phenomenon plays a key role in determining how a drug is spread throughout the body. You might be wondering, how do we categorize drugs based on these phenomena? Enter the BCS classification. Picture a puzzle with 4 pieces, each representing a different category of drug behavior. This is the BCS, or biopharmaceutics classification system. And just like a puzzle, it's a tool that helps us piece together a clearer understanding of how drugs behave in the body. The BCS classification was developed by the Food and Drug Administration, or FDA. And it's a system that groups drugs into 4 classes based on 2 key factors: solubility and intestinal permeability. Class 1 drugs are both highly soluble and highly permeable. These are the extroverts of the pharmaceutical world. They dissolve easily and pass readily through the body's membranes. Examples include drugs like metoprolol, a medication used to treat high blood pressure. Class 2 drugs are the introverts. They are poorly soluble but highly permeable. They don't dissolve well in water, but once they do, they are readily absorbed by the body. Drugs like ibuprofen fall into this class. Class 3 drugs are highly soluble but poorly permeable. They're like the wallflowers at the party. They dissolve easily but have a harder time getting through the body's membranes. An example is ranitidine, a drug used to reduce stomach acid. Finally, Class 4 drugs are poorly soluble and poorly permeable. These are the hard nuts to crack. They neither dissolve well nor pass easily through membranes. A drug like furosemide, used to treat fluid buildup, falls into this class. So why is the BCS classification important? Well, it helps us predict the drug absorption and bioavailability. It's an essential tool in drug development, helping scientists design drugs that are safe and effective. By knowing the BCS class of a drug, we can predict how it will behave in the body, how quickly it will be absorbed, and how much of it will reach its target site. The BCS classification helps us predict the drug absorption and bioavailability, making it a vital tool in drug development. As we conclude, let's summarize the key points of our discussion. Solubility and distribution phenomenon are foundational concepts in the realm of pharmacy. They're the invisible forces that govern how drugs behave in our bodies. Solubility, as we've discussed, is the ability of a substance to dissolve in a solvent. It's like how sugar dissolves in your cup of coffee, turning it sweet. In the pharmaceutical world, a drug's solubility can greatly influence its effectiveness. A drug that dissolves well in the body's fluids can be more readily absorbed and utilized. On the other hand, the distribution phenomenon refers to how a drug spreads throughout the body after administration. Imagine it as a guest entering a party and mingling with everyone, reaching even the farthest corners of the room. Similarly, after a drug is introduced into the body, it travels and interacts with various tissues and organs. This distribution is crucial in ensuring that the drug reaches its intended target and carries out its therapeutic effect. Now, where does the biopharmaceutics classification system, or BCS, fit into all this? Well, the BCS is a vital tool that categorizes drugs based on 2 factors: solubility and intestinal permeability. It gives us 4 classes of drugs, each with unique characteristics that dictate their behavior in the body. Understanding these classes helps pharmacists predict how a drug will behave in the body post-administration. It's like having a roadmap that guides us in drug design and development. In essence, solubility and distribution phenomenon are the unsung heroes of pharmacy. They shape the behavior of drugs, influencing their absorption, distribution, metabolism, and excretion. The BCS, in turn, offers a practical framework to understand and predict this behavior. So there you have it, a whirlwind tour of solubility and distribution phenomenon and their significance in the pharmaceutical world. And that's a wrap on solubility and distribution phenomenon. Subscribe for more because you won't find me later.